Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to nanoHUB-U. My name's Peter Brummel, and I'm going to be talking about nanophotonic modeling, specifically photonic crystal waveguides. This is lecture 1.5 in my class. So let's talk about periodic dielectric waveguides. So before we were mainly focused on what are the properties of 2D photonic crystals, okay? But then we also talked about how 2D photonic crystals can be contrasted with an index-guided waveguide and how it has different properties. But what if we could combine those two? Then that gives us actually some interesting possibilities. In particular, what that lets us do is we can take just 1D photonic crystals and then combine that with index guiding. And then we can actually get some of the same properties that we had for 2D and 3D photonic crystals, but just having to make periodic structure in 1D. And so then that actually could be very advantageous. Now you can see here, there are 3 examples of the sort of 1D photonic crystal and then 2D waveguiding approaches that we could use. Okay, so in particular, this would be kind of like an index-guided waveguide, except you would cut like a periodic array of holes inside, right? So this is kind of the most closely resembling standard technology. Or you could actually add ribs to the side of the index-guided waveguide. And another possibility that might seem actually like kind of surprising that it could even work would be to kind of do the reverse of that first structure, and then actually instead of removing holes, to actually cut away everything except like the small amount of rod and have it periodically connected. And so actually what may be surprising is that when you start to do this, you end up with modes that are like strongly connected to one another and will be highly propagating, even with gaps in between them, physical gaps. And so let me show you the band structure results that you can calculate in MIT Photonic Bands, MPB, in order to prove this. And this you can do by yourself using the MPB simulator on nanoHUB. So what you see here is when we plot the frequency versus wave vector, first of all, modes that are above this range here, okay, we call this the light line. So anything that's above this is not going to be index guided. And that's kind of the most fundamental principle of index guided modes, which is that when the lateral wave vector is too small, it will not be confined inside that waveguide, so it'll just escape to air. But if we do confine ourselves to be below the light line, then we have, like for a standard index guided waveguide, just a few modes. And so then this shows like kind of like what's the fundamental mode. It's like an even band, and then what's the odd band. And so this is covered kind of by standard like waveguide theory. So this is nothing new. However, what's interesting is if you actually start to create air gaps periodically in that original structure, then first of all, that changes the overall light line because of the new symmetry that you've introduced into the structure. And so first of all, you see that the light cone kind of gets cloned over here, right? So that's the first change. But then the second change is that the even band that I talked about earlier is also going to be reflected back, just like before. And you have the odd band up here, which is also reflected back. But then in between those, you actually have like a band gap. And so this band gap exists, but also if you disrupt the band gap by creating defects in that mode, then you can confine light to that specific place, which might not really seem reasonable, like to do that in index guided mode, but it is possible with a photonic crystal. Okay, so let's look at that in a little more detail. What happens when you introduce this point-like defect? So what you can see here is you effectively take a either the structure that I just showed you, which was basically the waveguide with all those like air gaps introduced, or you can introduce like a set of holes if you want it to be a little less radical. But then the point is that like right in the middle, you can see either here or here, right in the middle, then you're introducing like this kind of distortion from the standard periodic structure. So this is your defect. And then this defect is helping to confine light within that band gap frequency to that specific position. And what you can see is that light, as it goes away from this structure, decays exponentially. So what that tells us is that we're going to be able to use this both as like a radiative source and then also like kind of like a intermediate state like for some sort of tunneling mechanism. And so then this could be used like, for example, as like kind of a high quality factor resonator, for example, or it could be used for achieving like narrowband transmission. If you added capability of changing the refractive index or the geometry in some way, then it could also be tuned to transmit different wavelengths depending on your tuning parameter values. And then these are all things that can be calculated with MPB, like what the states are. However, there's one thing that would be hard to calculate in MPB directly, which would be the quality factor of the cavity. And so then that will reserve that discussion for later in the class. Okay, so now let's talk about another kind of hybrid structure that's really interesting. We call this the photonic crystal slab structure. And so the idea is that we had a lot of really cool physics and behavior that we observed in the 2D photonic crystal, but we had a big drawback, which was that the 2D photonic crystal that we modeled essentially was infinite in the z direction. Now, obviously, we can't really create an infinite photonic crystal as much as we might like to, so we always have to cut that off at some distance. But the question is, how much do we have to cut it off? I mean, do we have to have something that's like 10 meters tall, or can we actually make it like much thinner and still get like good properties? So the point of a photonic crystal slab is to say, like, let's not constrain our ambitions too much and try to make this really thin, like on the nanoscale in all directions, including the thickness. Okay, and so now what we're doing is essentially using index guiding in like this z direction in order to prevent light from coming out to the top and bottom. And so that will work as long as like our photonic crystal slab is enclosed by a lower index medium in general. However, if you took like very low index media for both the high and low dielectric and then surrounded it by like say silicon wafers or something, it might not work so well, right? But basically what you see here in both of these diagrams is a rod-like square lattice that's kind of being compressed to kind of a nanoscale height. And then you also see here on the right-hand side, essentially a very thin wafer that has holes cut into it, like in this triangular lattice pattern. And so this combination of the photonic band gap in the plane and then index guiding out of the plane should allow us to have like very well localized and high quality factor modes. And so here in this next diagram, I'm basically kind of extending the concepts that we talked about earlier with the light cone, where we said that anything that's like above the light cone is not going to be index guided and therefore will escape. And then we'll focus on the modes that are like below the light cone. And so what that tells us in particular is that when we have this photonic crystal structure, then we go from something that was analogous to that like 1D slab type waveguide that we had before to something that looks like kind of a cross between the 1D slab waveguide plus the 2D photonic crystal band structure that we calculated in the last lecture or so. And so what that gives rise to ultimately is band gaps that are very similar to what we had in the 2D photonic crystal as long as we're below the light line. And so that means that for the rod-like photonic crystals, slabs, then we can still have TM-like gaps. And then for the hole-like slabs, then we can have TE-like gaps. And then also we can increase the radius of those holes in order to have like a TE and TM-like band gap at the same time. So we're not necessarily forced to choose just one polarization or the other. Of course, it requires more work to get both. But then that's something that band structure calculators like MPB can give you. And so also, if we start to introduce defects into these photonic crystal slabs, then not unlike with the waveguides that we saw earlier, we can kind of guide light in the directions that we want it to go in 3 dimensions now, instead of just 2. And so you can see here, if we introduce like a series of defect rods right down the middle of this photonic crystal rod-like slab, then we have a path for the light to follow right down the middle. And from above, it kind of looks very similar to what we saw in the 2D photonic crystal. And then if we look at it from the side, then you can see that the light is strongly confined to the defect rods like vertically as well because of index guiding. And so overall what we've done is we've created a low loss waveguide. And then there are basically 2 sources of loss, one of which will scale as 1 over the group velocity. And so of course as the group velocity goes down, then this loss per unit distance will go up. And then there's a small but sometimes non-negligible component that goes as 1 over the group velocity squared. Okay, so then that's like the only possible drawback to these kind of slow light modes, which is that if you need to propagate over long distances, then the losses can become higher, but they don't necessarily have to be extremely high. Another thing that you can do, not surprisingly, is just have a single defect. So if you have a single defect, then you can localize light very well. And in particular, you can have a mode that looks like this from above. So you can see that this is kind of like the monopole type mode that we talked about last time. And it has like exponential decay, both in the x direction and the y direction, as you can see from above. And then if you look at it from the z direction, then it has also very strong confinement, not just in this y direction, but also in the z direction, top to bottom. And so this is creating a very high quality factor mode. So in other words, a mode that will survive for a very long time compared to the period of the optical oscillation. And so now we can actually see that it's not necessarily as straightforward as just put a defect in there and then get a high quality factor mode automatically. In fact, it's very sensitive to exactly how are we going to do this. And so you can see that there are basically 2 types of approaches that you can use to introduce defects. One in which you basically just introduce a single point-like defect, and then the other where you introduce kind of a cross, which is like 5 different rods that are all changed at the same time, just in terms of the dielectric constant here. So I haven't actually considered what happens if you change the radii. But what you can see is that as the index contrast goes like from a very large value, like here delta epsilon is -7, and then you reduce that a little bit to lower and lower values, then the quality factor also tends to go up. But the drawback is that the localization is not as good. So then you have kind of this trade-off in some sense between localization versus quality factor. And then the other thing about that trade-off you can see here is that the cross-like pattern or structure behaves much better. So you get about a factor of 10 or so in the quality factor associated with having this cross and the corresponding like factor of 5 type delocalization that's introduced using this cross method. And then in terms of the quality factors that are being achieved here, I think if you consider the fact that these monopole-like modes are pretty much as small as you can get using conventional light, then the quality factors like approaching 1 million are quite excellent. So in other words, that means that you could oscillate at least 1 million times before you lost most of your energy, or to be more specific, about 27 decibels worth of energy from the original source. So that's like very good for a lot of potential applications, like detecting very small amounts of chemicals, or possibly something that's like very sensitive for optical clocks, or there are many applications for these. So let's look at an even more sophisticated application. So here I'm demonstrating what we call the micro add-drop filter for photonic crystals. So the idea is that if you have two waveguides that are coupled together using like a pair of defect resonant cavities, then if you design everything just right, then you can actually get it to just couple a single wavelength from this upper waveguide, which is represented schematically here, and then like actually implemented here as like a missing row of rods. And then you can couple just this one wavelength down to the second waveguide, which is the second missing row of rods, through this set of resonances. And so the idea is that these two resonators interact so that the coupling only happens like at a very specific wavelength which you're interested in, which also could be thought of as like very high quality factor mode state. So if you had low quality factor, you couldn't even dream of doing something like this. And there are potential applications for this sort of technique, both in telecommunications, like for dense wavelength division multiplexing, for example, and then also applications in terms of optical comb generation and many other things where you need to have a fine discrimination between nearby wavelengths. So now I think we talked about photonic crystal fiber a little bit before, but I just wanted to show you in detail now that we talked about it. Like the waveguiding effect can be translated into having the photonic crystal band gap in the XY direction, and then you can have basically the waveguide or the photonic crystal extend for a very long distance. So it doesn't always have to be a slab. So you can make this photonic crystal fiber like a slab, but you can also make it very long. You can make it potentially like many meters. And then there are all kinds of cool applications for this. So I think I said detecting like dangerous chemicals, but another really interesting application is called dielectric laser acceleration, where the idea is you create a strong optical field and then you would allow subatomic particles like electrons to propagate inside this hollow core and then accelerate them using light. So hopefully that gives you a good sense of what is possible to calculate with band structures, like not just kind of like the basic mathematical principles, but also like what kind of code can we use, specifically MIT photonic bands or MPB, and also like what are some of the detailed applications which can include like chemical sensors, like wavelength division multiplexing, and photovoltaics, thermophotovoltaics, many other topics. And so next week, we're actually going to look at kind of a different solution technique that in many ways is complementary to what we've already done, which is multi-layered photonic systems. And we're going to use the transfer matrix or rigorous coupled wave analysis formalism in order to achieve that. And in order to kind of prepare yourself, you may want to look at Joe Nopolis' book in Appendix D, which kind of gives an overview of some of the computational techniques available for these sort of nanophotonic systems. Thank you.